First law of thermodynamics. So, I like that response. So we're going to talk about what a thermodynamic system is. It's basically a system, but in the context of thermodynamics. We'll talk about work done again. So remember, how did we calculate work last time we talked about work? Well, kind of, yeah. That's one of the. If you have a graph, how did you calculate it?
The area under the force curve.
Yes, the area under the force curve. What kind of graphs are we dealing with now? What are the axes?
Temperature.
Pressure?
Yeah.
Pressure and volume. Okay? So it'll still be the area under the curve, but it'll be the area under the PV diagram curve. Okay? So we'll talk about why that is in a little bit. Talk about paths between thermodynamic states. That's just the lines that connect the dots on the PV diagram. Internal energy. Remember, internal energy is the same as thermal energy. So that's any of the stuff that we treat as measurable by temperature. Okay. And then we have kinds of thermodynamic processes. We've already talked about some of these, but we're going to go into a little bit more detail about the math and how we get back and forth between them. And ideal gas, ideal gas, ideal gas. All right? All right. We can do this today. So, let's talk about a thermodynamic system. Here is a thermodynamic system. Anybody know what this is? Yeah, it's a popcorn kernel, okay? So, what do you put into the system? Heat. All right? So, you put heat into the system. All right? That means hot oil, right? So, you want to do like the movie style, you do the hot oil, or you just put it in a microwave and then you add heat by vibrating the stuff inside of it, okay? Then work done by the system, okay? Because, right, the popcorn kernel is a sort of a hard container. Once you get it hot enough, what does it do? Explodes, okay? So pressure builds up inside of the kernel, it pushes the shell out, and then you have a tasty snack, okay? So you add heat, that means there's work, and that is your thermodynamic system, all right? Now here you'll notice the boundaries of the system don't have to stay the same shape and size because the popcorn kernel, once it explodes, that's still the system, but now it's bigger, okay? So let's talk about work done during volume changes. So if you change the size of your system, that's a change in volume, all right? So remember, this is what work used to look like. So we have this force versus displacement or force versus position graph, okay? So if you graph force versus position, it looks like this. If you want to know the work done from here to here, what do? Take the integral, which means figure out the area under the curve, okay? So that's the work, all right? Now let's talk about what we're using in thermodynamics. So we have a PV diagram. Let's say we have one that looks like this. So here's our PV diagram. What kind of process is this? Which thing's not changing? PV, T?
Oh, heat's changing. Or pressure's changing.
ISO what?
Isobaric?
No, because that would, isobaric would be flat.
Oh, okay.
Isochoric would be vertical. This is the other one. Isothermal expansion. Okay, so this is an isotherm. You see this like inverse curve looks like an isotherm, and then it's an expansion because it's going from a smaller volume to a bigger volume. It's going this way along the volume axis. Okay, so here's your isothermal expansion. All right, so how are we going to calculate work? Well, let's go back to what we had before. Okay, work was F dot dx. Okay. What do we know about pressure? How do we define pressure? Force over area. Okay. So the force divided by the area gives you pressure. So if you have force, you can write it as pressure times area. Okay, it's just rearranging things. So we end up with the integral of pressure times area dx. Okay, you take area and you multiply it by another length, what do you get?
Volume.
Volume, right? This is meters squared, this is meters, now you have meters cubed. This becomes PdV, okay? Which means, if you have a PV diagram, how do you find the work? Yeah, area under the curve, okay? So the work done by the gas, right? The force is the gas here. You can see it's doing work. It's the gas is pushing the piston this way. So the force is this way, the displacement's this way. That should be positive work, okay? And you can calculate it from this graph by looking at the area under the PV curve, all right? So just like work before, work's going to be positive and negative in the same way. So if this were an isothermal compression, would work be positive or negative? Negative, okay? Because the outside, right, the force from outside, the pressure from outside would be doing work on the system. It would be pushing the piston in, okay? In this case, because the gas is pushing the piston out, it's doing the force, okay? And then it's going in the same direction as the displacement for the system, all right? So yeah, you can see, just like before, you're looking at force in the direction of dx, and this is your work. So this is the work done by your system, all right? The work done by the environment would be the force pushing this way, okay? This is the force from your system, this is the force from your environment. Depending on whether those are going in the same direction as your displacement tells you whether you have a positive or negative work. Yes?
For isothermic, is the pressure always constant?
Does it look like it's constant?
No.
So for isothermal, pressure and volume change and only temperature stays the same, right? And you can see here at the initial point, we have a pressure and volume that's different from our final pressure and volume. Yeah. The only thing that stays the same is temperature. It's a good question. All right, so this is what I'm talking about. Here we have, this is the force from your gas, right? It comes from inside where the gas is. This is the force from the environment. It comes from outside. Depending on which force you're talking about, depending on which work you're talking about, right? Work system goes one way, work environment goes the other way. So let's say we wanted to have a compression, okay? That means we've changed the direction of this arrow. The curve's the same. We're going from the same, between the same two states, but now we're going in a different direction, okay? So it's still the same area, but what is your work in this case?
Negative.
Negative, okay? So if you go this way, it's going to be positive. If you go this way, it's going to be negative. And that's the work done by the system, okay? What's the sign of the work done by the environment? Positive, okay? So it's just a matter of, just like before, is your force going in the same direction as your displacement? All right? So remember, whatever your work system is, the work environment's going to be the negative of that, okay? Because these forces always oppose each other, so you just have to figure out which one you're talking about. All right. Here's a question. We're mostly thinking it's either positive, negative, or zero. So please discuss, and we'll put again. Better, yes. Zero, huh? So the work done by the system is going to be integrated from here to here. That's going to be a positive value, okay? And I just want you to remember, anytime you have an expansion, right, that means the work done by your system is positive, because the way to expand the volume of the piston is that the gas inside has to push the piston. So if the gas is displacing the piston, it's always going to be positive. Yes?
But if there's no increase in the pressure, then how is there an increase in volume?
Well, there's probably an increase in temperature, and as you do that, if you do that nice and slow, right, there'll be a microscopic increase in pressure, but then the volume changes. And so we treat that as though the pressure is not changing. Although I think if you measure it at like a small enough scale, you'll see there's minor pressure changes, but then it compensates, right? So yeah, it's a little bit more complicated than that. Okay, here's another question. Okay, let's just. Okay, one more person got the right answer. So, which way are you? What are you? Are you the system or the environment? You're the environment. Which way are you pushing? Down. Which way is the piston moving? Down. Okay, so that means the work done by you, the environment, is positive. All right, the gas pushes which way? Up. Right, the pressure is always going out in all directions. So the gas is pushing the piston up, but this is being displaced down. So if it asks for the work done by the system, that would be negative. Okay, so since you're the environment, you're moving in the same direction as the displacement. The environmental work is positive. Okay, system work would be negative, but you have to be careful because we're going to start switching back and forth between work done by the system and work done by the environment. So you have to pay attention to which one it's asking about. Okay, all right. The kids ganged up on me last night. Oh, well, we're not that good, so let's try again.
Probably need to.
Okay, we're thinking. So I just want you guys to think about what these graphs look like, okay? So if we have a PV diagram, what does an isobaric curve look like? Straight, right? So that's going to have work that looks like this, okay? What about an isotherm?
Where?
It looks like this.
I said
So
that.
you can take an area under that, it's going to look like this, all right? What about an isochoric graph? That's vertical. What's the area under that? 0, okay? So isochoric, there's no work, right? Because remember, every time we're doing work, we're talking about this piston, it has to change volume, right? The gas has to either push the piston up or the environment has to push the piston down. But if you don't change volume, the piston doesn't move. If the piston doesn't move, the displacement is 0, and the work done is 0, okay? So how are we changing, if we're not doing work, how are we changing things like temperature or pressure? What other things do we have to work with? Well, we have work plus heat. What's the other one? Well, there's work and there's heat. Okay, you can add temperature with heat. You don't have to use work, okay? So if you want to change the temperature, you can just light a fire, all right? And that's not doing physical work, that's just adding heat to the system. Or you can put it on ice, and that's taking heat out of the system, okay? In an isochoric change, pressure and temperature change, right? So yeah, isochoric, pressure and temperature change, but volume is constant, right? In isothermal, pressure and volume can change, but temperature is constant. Isobaric, pressure stays the same, and temperature and volume can change. Yeah, okay. So isochoric, okay, that's the only one where work is 0, all right? Okay, so here's a problem that we're going to do. We're going to figure out how much work is done on the gas in this process shown below on the graph. A couple things to remember here before we even get started, and of course I want you to do this problem on your own before watching the solution. Before we even get started though, we want to know, is the work going to be positive or negative? And in order to know that, we want to figure out, okay, this is the work done on the gas. Okay, so is that work going to be the environmental work, or is that going to be the work done by the system? So what is our system in this case? So the system is the gas. So the environment is outside piston or gas, okay? So this is going to be, we're looking for work environmental, all right? And that's the work done on the gas, so that's the outside work. Because this is an expansion, that means we know the gas, the system, is doing the work. So the environment, right, so that the system work should be positive because the gas is doing the work. The environment work should be negative, okay? And this environmental work is negative because the gas is doing the work. So it's pushing the piston out. So that means the force is in the opposite direction, right? The force for our environmental work, which should be down, is in the opposite direction, assuming we have a piston in this case, right? So let's see. That means the environmental work should have a force pushing down, but the gas and the displacement are both up. So this piston moves up, and that means the volume gets bigger. That's why it's an expansion, right? Because we're moving in this direction on the volume axis. And that's why we know that the work done by the environment has to be negative. Okay? So getting rid of that, we know work environment is negative, just to get started. Okay, now that we know that, we know our answer should be negative. So when we're at the end, we need a negative answer. Now we just have to calculate the work. And the work in this case is the area under the curve. And we can either go through this whole process of figuring out the equation of this line and then integrating from here to here, and then figuring out this and integrating from here to here, or we can just remember that this is an integral, and graphically what that means is that we just need to calculate the area under the curve here. And that's the easiest way to do that, is to split that into a triangle and a rectangle. And then we also need the area here, and that's just a rectangle. So we're going to calculate this area and we're going to calculate these two areas together. And the only other thing we have to really be careful of here is units, because you can see we have kilopascals and centimeters cubed, so that makes things a little bit trickier. So we're going to have to convert to pascals and meters cubed, because that's what we use for PV equals nRT and all of our units in physics. So to start out with, we're going to calculate this area. So that means the work done in this section, which is and we care about the environmental work. So that's going to be negative, okay, because we already decided that's negative. That's going to be the rectangle part, so this part. We need base times height, so that's a distance of 100 kilopascals, so 100 times 10 to the third pascals, that's this height, all right, times our 500 times 10 to the negative 6 meters cubed, okay, because remember, a key thing to remember here is that 1 centimeter cubed, right, so 1 centimeter cubed is equal to 1 times 10 to the negative 6 meters cubed. The reason for this is 1 centimeter, right, is equal to 0.01 meters, and then you cube both sides, and this ends up with 1 centimeter cubed is equal to 0.000001 meters cubed, okay? So that's where that comes from. That's the standard conversion. So don't forget about the cube, all right? Then we want to calculate the area of this thing. So that's going to be plus, it's still a negative 1/2 base times height. So that's going to be 200, right? That height is 200 times 10 to the third pascals times, once again, 500 times 10 to the negative 6 meters cubed. So when you sum all that up, that's going to be negative 100 joules, okay? So this is our first value. That's the value of this area right here, All right. Then we're going to calculate the area in the pink section. So the work environment here, environmental work, still negative, right? Because we're still saying the gas is doing the work and that environment is outside the gas. Then this is just a rectangle. So 300 times 10 to the third pascals, that's the height. And then 500 times 10 to the negative 6 meters cubed, that's the width or base. And that gives us negative 150 joules. Okay, so our work total is going to be both of these things added together. So negative 100 joules plus negative 150 joules gives us negative 250 joules. So the work done by the environment total, that's the net work done on the gas, is going to be negative 250 joules. And we'll just highlight that because that is our answer. Now, if you do this from an integration perspective, you just have to know that the dot product gives you the negative sign because the displacement is the opposite direction from the force. But remember, we just used our knowledge of physics to figure out that we're going to get a negative answer right from the get-go. So you don't have to necessarily figure out how to get that the mathematical way. As long as you know the physics reason, that's good enough for me.